Okay, so Assalamu alaikum and hi. This is Sayyid Mohammed Shafi from SP and DUT, and we have come up with our Pet for Talk episode 3. This time we'll be going towards the drilling engineering section, and in which there is a technology which is known as high drilling wells, which requires a bit of new technology and new techniques which are used by different companies. And here we have someone who is very specialist in this ERD wells, which are used to increase the productivity of the wells and to tap the zones which are not conventionally drilled. So we have Mr. Neil with us, Mr. Neil Armstrong. Don't consider him as the one who has gone to the moon, but he is the one. But he is the one who is working in the Scottish company Merlin ERD and has past 20 years of experience with ExxonMobil. So, Mr. Neil, I'll be handing over it to you, and you can have your session.
Great, thanks very much, Saeed. Thanks very much for inviting me to speak. It's a pleasure. So I put together this presentation with the aim of identifying the main root causes of drilling problems, drilling events, so that we could share the learnings and make sure we could try and avoid the pain of planting BHAs in the ground in the future. Doesn't benefit anybody. It makes it makes operators much more cautious. It makes them much more conservative, adding MPT to wells that they're planning. So really, it then makes some more challenging wells almost impossible to get through the approvals process when there's so much contingency in the original planning basis. So the objective is to share learnings, try and eliminate some of these problems, and generally improve drilling performance. As an industry, we're really not very good at learning from mistakes. We don't tend to invest enough time in thoroughly investigating problems. And we tend to ignore near misses as well. And there's a lot of value in the near miss events. We tend to just think, we got away with that one, let's move on and plan the next well. When in actual fact, really, we should be thinking, we were very close on that one. We need to look closely at what went wrong there, because that could have easily been a major NPT event and potentially losing a BHA or a whole section. So really, we need to focus a lot more on thorough analysis of near misses and problem events. So I'm going to be talking here about a lot of problems that other operators have had worldwide. They come to us with their problems, and then we try and do a good detailed analysis and give them recommendations to avoid similar problems in the future. So I'm not claiming to be completely immune from these kind of problems. I'll be honest, I've planted 3 BHAs when I've been a lead engineer on a well in my career. 2 of them in the North Sea in the UK, and 1 of them's planted offshore California in the US. So I'm not completely immune, but I've seen a lot of stuck pipe events in my time as a drilling engineer, and I've seen a lot more in the last 7 years since I've been working with Merlin ERD. And we looked at the last 50 problem events. So these events spanned a 10-year period. All of them resulted in, as a total, it was a result 50 BHAs lost in hole. And we estimated that's about $250 million of lost in hole cost. So that's just a rough estimate based on a fairly cheap BHA. But that totals more than $1 billion worth of MPT costs. Because if you think about it, you're losing a BHA in the hole. That's often a small part of the cost. The major part of the cost is all the time spent recovering from that event, plugging that hole back, sidetracking, and then drilling back to where you were before. Often eclipses the cost of the BHA. And all of these events were avoidable. I'm showing a day's depth plot there on the right, where red was obviously the planned days, the budget days versus depth, and the blue is the actual. So that well celebrated its birthday at around the sea there towards the end, with another tool failure. So it went way over budget, about 200 days over plan. So we see some pretty spectacular failures. We claim they are all avoidable. So I'm going to spend a lot of time talking about problems. However, I'd just like to spend a couple minutes talking about what happens when it all goes right. So this is a nose plot. This is the standard industry envelope that shows what's been achieved on high angle wells. So all of the grey dots represent a well that has been drilled by an operator somewhere in the world. The grey outline highlights the envelope of what's been achieved worldwide. So you can see out to the far right of the nose plot, you've got a well there. It says ExxonMobil Sakhalin 05 RD. So that is currently the world record well for step out and also measured depth. So the same operator has drilled 10 out of 10 longest wells in the world by measured depth. All of them are greater than 40,000 feet. One of them, which was the world record well for a while, was drilled with less than 1% NPT. I think it was 6.6% NPT. And these are not simple wells, maybe like a well through, one of the wells that was world record well for a while was the Maersk well in the Persian Gulf, the Al Shaheen well. It was over 40,000 feet measured depth, but it was a barefoot completion. It was an 8.5-inch hole section through the Upper Zarkham Reservoir, which is carbonate, and they drilled 8.5-inch hole section until they ran out of drill pipe. And it was a barefoot completion, whereas these wells in Sakhalin Island, they're running screens into these wells, which is challenging because you can't rotate those screens. You can rotate some screens without damaging, but most screens you don't want to rotate them because you'll either damage them mechanically or you'll plug them with solids and then they won't perform as expected. So the point is, they're very challenging wells, all world record wells, but they're drilling them, some of them, with less than 1% NPT. And how are they able to do this? Well, they're able to do it because they build on lessons learned. They've got a team that's fairly consistent. They've got a regular program, so there's no gaps in the program. They're not losing personnel, losing knowledge. They've got the resources they need in terms of they've got one of the most powerful rigs ever built, land rigs ever built, which was the Yastreb rig. But they've also got 2 offshore platforms with similar drilling capabilities. So massive pump capacity, massive top drive capacity, tailor-made drill pipe. So they've got all the resources they need. But the key thing is, you can get into a lot of trouble with a big rig and fancy drill pipe. The key thing is that they've built on lessons learned and they've learned from their mistakes. So hopefully you guys can learn from other people's mistakes through this presentation.
Yes.
So I'll not do that because it didn't show up the last time I did it. So after reviewing all of these problem events, the ranking came out like this. So the top event was operational practices. That was the most common root cause. So high risk operational practices. And I'm going to talk about each of these in a little bit of detail. I'm not going to go into the solutions to all of these problems, because that would probably be several hours on each item. And we're going to try and get this done in the next 45 minutes. So I'll just highlight what the main issue was related to each of these. And we might talk about some solutions as well. So yeah, wellbore stability, well up that list. So compressor failure of the wellbore. Operating limits and planning. So really we're talking there about where you've planned a well, you've expected certain limits, maybe geological limits, for your fracture gradient, and it's turned out to be incorrect, or pore pressure or wellbore stability, mud weight requirement, and it turns out you're using inappropriate or inaccurate information for planning the well. And then also operating limits of equipment that's either not known or incorrect. And then differential sticking, which is fairly obvious, hole cleaning, equipment failure, hole geometry, or borehole patterns. So this is kind of how it breaks down percentage-wise. So operational practices were quite well out there in front, and then almost joint second and third were operating limits and wellbore stability, and closely followed by differential sticking and then hole cleaning. So I'll mention a couple of things that make our sample. Obviously, this is our sample from 50 problem reviews, but it's worth noting that we don't tend to get the basic, equipment failures where it's obvious, what's happened. A tool's failed or something like that. We don't tend to see those. And it's actually unusual for one of those to create a stuck pipe event. But we don't tend to see them. They tend to be more, they're more obvious. We get the ones that require a bit more of an investigation. So another thing was we had one operator that had they gave us to look at their, 9 of their most troublesome wells over a 2-year period. And they had 7 differential sticking events, 4 of them resulting in lost BHAs. So they kind of distorted our differential sticking figures a little bit. So it's maybe slightly higher, a higher percentage of differential sticking than it would be if you had a broader set of data to analyze. But anyway, the actual numbers and the relative probability of occurrence or regularity of occurrence is really not that important. So we'll talk about each of these one by one. So, operation practices. So here we're talking about practices that mitigate the risks in the well. And it's surprising how often we find when we look at these events that the drilling engineers or the planning team have actually identified a lot of the key risks on the well, almost all of them. When we look at the drilling hazard ID or the drilling risk assessment, we see generally the listing all of the main risks, often the risk that's resulted in often the risk that's caused the stuck pipe event. But the key gap is then transferring that risks to then applying mitigators in the operational practices to mitigate those risks and avoid the occurrence of a major problem event. And it generally relates to connections and safe connection practices. Often what you do if you have a failed survey, so we saw a couple of differential sticking events where survey failed, and rather than moving the pipe and then repeating the survey, a survey was just repeated, the pumps were just recycled, which resulted in a lot of stationary time and a differential sticking event. And then tripping practices. Now this is the major one, and it should really be top of the list there. A lot of problems on tripping, and a lot of the time it's just pulling tight and then continuing to pull. And it sounds really simple, and people will be sitting shaking their heads and saying, how are people still doing this? Well, it still happens. Pull limits are not clear in procedures, so how high, an oval pull can the driller apply before he has to trip back in hole and then deal with the issue. And then back reaming. Back reaming, probably one of the highest risk operations you can do. It's very easy to get yourself into trouble. You know, if you think about it, you're moving pretty much all those cuttings are being moved uphole with the BHA. So if you're pulling too fast, or you move into an enlarged section of hole where you mobilize a large volume of material, then it's very easy to get packed off when backreaming. So we try to avoid backreaming as much as possible. But there are legitimate reasons for backreaming, and if you have to backream, you just make sure you do it by following some basic procedures to ensure it's done safely. So, wellbore stability. So we see a lot of wellbore stability problems. Often operators coming thinking they've got a hole cleaning problem. In reality, they've got a wellbore stability problem. You know, they think they're trying to clean 16-inch hole, but they've actually got 26-inch hole down there, and their flow rates are just totally inadequate for cleaning that enlarged hole. So the priority is, or the key mitigator is running an adequate mud weight for wellbore stability. So you can invest in a geomechanics study, which will give you a recommendation for a mud weight, and that then should allow you to avoid compressive failure of the wellbore, which is what we're talking about here. The geomechanics inputs are extensive. The geomechanics report is pretty expensive and quite time consuming. But the final output is often just a mud weight, and that is it. So, you know, if you don't have enough data for an adequate geomechanics study, or the time, or the funds, then you should really just run the highest mud weight you can, and prioritize wellbore stability over losses. When you've got an unstable wellbore, when you identify your wellbore's unstable, by then it's often too late. You've got cuttings, you've got cavings coming over the shakers, the hole is already enlarged, and then you're stuck with it. It's irreversible. So it's not just related to mud weight, but it's also related to mud inhibition. It's rare that we'll see an inhibition problem with oil-based mud. It's normally a water-based mud issue, and a mud system, KCl mud that is designed to be inhibitive, but it's not doing its job. And then, of course, swab-induced instability. So your mud weight might be adequate while drilling, it might be adequate while the pipe's stationary in the hole to maintain a stable wellbore. But then once you start introducing swab pressures, then you swab below the stability mud weight and you bring the wellbore in. So with swab, what we see is operators not really giving swab, is giving tripping speed limits to drillers. So the driller doesn't know how fast he's allowed to trip. He thinks he's doing a good job by tripping as fast as possible, or he thinks once he's encasing, then he's safe and he can trip as fast as possible. But even if you're encasing, the pressure that you're inducing through swab is still seen by the bottom of the hole, or a potentially unstable section of hole. So that's fairly common. You know, and a way to diagnose that is the hole is stable while you're drilling it, you trip out a hole, go back to bottom, and then you're finding issues with the hole. And that's often an indicator that you've either got some sort of time-based instability, or you've swabbed the hole, you've swabbed below the required mud weight for wellbore stability. And I mentioned time-based instability there. Now, you're only going to have time-based instability with water-based mud. Oil-based mud, it's unless the mud system is breaking down, your emulsion stability is breaking down, you're not going to have a time-based issue with oil-based mud. Now, wellbores have been left for months with water-based mud in the hole. You go back to them and they're still they're still in perfect condition. Where the hole seems to deteriorate over time when you've got oil-based mud in the hole, it's normally because of the swab and the surge. It's the operations you've been doing in that time rather than the time itself. Okay, and then operating limits. So this is quite an interesting one because we're talking about a few different things here, a few different causes. So equipment limits. It's not unusual for us to see the guys in the rig using different limits to what the drilling engineer planned the well using. So what I'm talking about there is it might be just as simple as the drill pipe limits, you know, the torque and the tensile limits for the drill pipe. So I'm showing this chart down at the bottom left of this slide, which is showing a combined loading plot for some 5 7/8 drill pipe on a well. And the curves show the body operating limits. So the bold line, the bold maroon line is showing the maximum operating limit for the pipe body, assuming premium pipe, so 80% remaining body wall. And then the dotted blue line showing a safety factor on that, so 20% safety factor. And then the very faint blue lines showing a 40% safety factor. And then the horizontal line going across, or the line that's slightly diagonal, is indicating the limit for the operating torque limit for the connection. So that torque limit for this premium connection decreases slightly. The operating torque limit decreases slightly as the tension or the hook load increases. So it's really useful to for the guys in the rig to really fully understand what that combined loading operating window is. So the green area is showing what would be a safe operating region for a combination of torque and hook load. And the black dots show how the pipe was worked for a stuck pipe event we investigated. So it turned out this was a differential sticking event. So if the driller had responded a bit more aggressively, if he'd known what his limits were, if he knew that he could operate in that green region safely, then he would have been a bit more aggressive about it, and he would have operated closer to his limits, faster, and stood a pretty good chance of getting free. We'll talk about differential sticking in a bit more detail, but the key point with differential sticking is when you're across a permeable zone in a high angle well with any pipe, you've got to assume you're getting differentially stuck. It's just a question of time. But it takes time for that pressure, the full differential pressure to build up. So if you respond quickly, then you can get free. But you've got to know your limits. We saw events where the driller's on the phone to the company man. What can I pull to? Company man's on the phone to town, just double checking. And by the time you've got an answer, it's too late. You've gone from what would have been just a short line item in the daily drilling report, tight after connection, pulled 60k over, pipe free. You've gone from that to a major NPT event just because you didn't know your limits. And then geological limits. So that's kind of what I mentioned earlier, where you think you've got a certain fracture gradient when actually it turns out it's less than that. You're unsure about what your wellbore stability limit is, your mud weight requirement is. So just being unaware of or having inaccurate information on your geological limits. And then modeling load. So modeling done either incorrectly or not done at all. So that could be anything from not accurately modeling swab loads or surge loads or whatever. and that's showing the chart on the top right is just showing a tension plot with some buckling limit shown. Okay, now this one's talking about differential sticking. So the key thing with differential sticking is recognition and response. So it just requires a bit of time being spent with the crew on reminding them how to recognize a differential sticking event, so they can then respond quickly, and then letting them know what should they do to respond, what's the best way to respond. So recognizing a differential sticking event is actually relatively easy. It's the only sticking mechanism that results in no pipe movement in any direction. You can't rotate the pipe, you can't slack off, you can't pick up. It's the only sticking mechanism that results in in full movement in full unrestricted flow after the stuck pipe mechanism, and also it's the only one where you've got full unrestricted flow after a period of stationary pipe. So in theory, you could pull into some hole geometry issue, so maybe a key seat, and have full unrestricted flow. But if your pipe's free, then you've got a period of stationary pipe. Then it's stuck. Then that's a sure sign of different. And you've got full unrestricted flow. Then that's a good sure sign of differential sticking. So training the crew on that, on recognition and response. Minimizing the contact area is a big hitter. So the little anagram down the bottom, stops, that's illustrating the recipe for differential sticking. So you need all 5 of those ingredients for differential sticking. If you could eliminate any one of them, then you could eliminate differential sticking. Unfortunately, it's impossible to completely eliminate any one of them in a high angle well. It's impossible to eliminate stationary pipe. At some point, you're going to have the pipe will be held stationary. The filter cake, inevitably, you're going to have some filter cake. Overbalance. Actually, you could completely eliminate overbalance. You could drill. You could use MPD. Permeable formation. We're often trying to drill through permeable formations because they're our reservoirs. So it's inevitable that you're going to have to drill through some permeable formation at some point. In surface contact area, even in a vertical well, at some point you'll have pipe lying in contact with the wellbore, because we never drill a perfectly vertical hole. But higher the angle well, the more pipe you're going to have in contact with the wellbore. Therefore, the higher the differential sticking risk. So the strategy is to minimize the risk, to avoid differential sticking, is to minimize the risk in as many of these areas as possible. So what we saw on quite a few problem events was differential sticking was identified as an issue, as a potential risk, but the only thing that was done to try and mitigate that risk was trying to reduce the overbalance. So a low mud weight was used. And we saw in a few instances where the low mud weight resulted in wellbore instability, and it still was not enough to mitigate differential sticking. So we actually saw the running low mud weight caused instability, and they still got differentially stuck. So, but the problem was the fluid loss was really high on the mud, so they had a thick and impermeable filter cake. The pipe was held stationary for too long over a connection, and the surface contact area was high. And the surface contact area, the big risk areas are your drill collars, or LWD tools, or non-mag drill collars, just simply because you've got more surface contact with the wellbore and the filter cake. And then the second highest risk area is your heavyweight drill pipe. and then after that it's drill pipe. It's actually pretty unusual to see a sticking event initiate at the drill pipe. It's almost always in the BHA or on the heavyweight, or even across jars and accelerators. So if running jars and accelerators, run them with some standoff subs on them. So hole cleaning, yeah, I mean we see a lot of problems with hole cleaning, and then we see quite a lot that results in stuck pipe events. The one problem is that the parameters are often adequate for the size of the hole or the size of the bit that's being used. Unfortunately, the hole is bigger than the size of the bit because you've got some sort of hole enlargement, often caused by wellbore instability due to inadequate mud weight. Sometimes caused by side cutting due to a sensitive formation, and you're doing a lot of rotation off bottom, so you've got lateral forces and side cutting. But almost always it's wellbore. It's a wellbore instability issue, so compressive failure of the wellbore. And tool rotary speed limits. So hole cleaning problems resulting from tools that are limiting the rotary speed. And the most common one would be a motor. So you're drilling a hole but you can't use a rotary speed that would be recommended for good hole cleaning. So one of the key issues there is it's often safety factors being put on safety factors. The motor provider will give the lowest rotary speed that they're comfortable at the motor being rotated at, when in actual fact the motors could be rotated safely at a higher rotary speed. Often with motors you'll have a rotary speed that's an RPM limit in the curve section, an RPM limit in a tangent, and an RPM limit off bottom. And you're often given the lowest of those options. Whereas you could use the lower RPM limit while you're drilling the curve, and then, or you're in a higher dogleg area, use the lower rotary speed when you're off bottom. But when you're on bottom and you're in tangent, use the higher speed and improve your hole cleaning. And then the low end fluid rheology. So most operators now know to focus on the 6 RPM, the 3 RPM, so the low rheology end of the drilling fluid, to try and increase that to get viscous coupling. So that's to allow you to pick up the cuttings from the low side of the hole to the high side of the hole, where the high velocity flow area is, and then that viscosity also in the fluid allows you to keep the cuttings in that high velocity flow area for a little bit longer than if the fluid was a lower viscosity. The issue often though is that the mud looks like it's got adequate low-end rheology at surface conditions, so surface temperature and pressure, that the mud engineer is using for his mud parameter checks. However, at downhole temperature and conditions, the mud is inadequate. It's too thin to clean the hole. So you can take fan 70 measurements of the mud to see what the actual downhole rheology is of the fluid. However, it's difficult to do that at the rig site. The equipment is normally in a lab in town, so you can either ship samples back to town to get it done, or you get it done before the job and see, based on your assumed temperature and pressure measurements. And then that's the best way to do it. You plan the well based on the assumed, and then when you're on the actual well and you've got some improved data, then you send samples to town and get it checked with the actual downhole temperature and pressure. And then equipment failure. So the equipment failures that we saw that resulted in stuck pipe events were almost all related to either the drill pipe, which really highlighted the importance of having good quality drill pipe that's been inspected properly and thoroughly. And if there's any doubt about any of the joints, that they're just laid out, and that they're managed properly at the rig site as well. So they're inspected, as they're coming out the hole, and that they're rotated around as well, so they're not always at the same point, in the high stress parts of the well. And then the other most common one was mud pumps. So liners failing, pumps going down. Anybody who's been involved with drilling will have experienced frustration of having to deal with failed mud pumps. So the stuck pipe events we've seen related to that are when you've been drilling at high ROPs, the hole's loading up with cuttings. You're in a tangent that's within the avalanche zone, between 35 to 65 degrees. Pumps go down, and you're stuck in an open hole. The hole's loaded up with cuttings. You've got nowhere to go. You either sit in the open hole and try and fix the pumps, or you try and get to the shoe with a hole that's fully loaded up with cuttings. And then top drive failure. So almost always wash pipes failing. This picture here, the picture in the middle, is showing the Dublin wash pipe system, which is now an NOV product, and that almost doubles the life of a top drive wash pipe. But yeah, I mean, even we've got a well that we're working on at the moment down in Australia. They changed out their wash pipe prior to a really high risk 12.25-inch hole section, and still the wash pipes failed. So yeah, it's kind of a weak link in the circulating system that can result in you getting stuck in open hole with the inability to rotate. So that's pretty much it for the equipment failure. So for hole geometry and patterns, so this is an interesting one. The most common tripping problems that are related to hole geometry will be related to ledges. Often caused by some source of instability. So you've got an enlarged section, and then you've got a gauge stringer, and then you're trying to pull through that gauge section, where you've got a stabilizer that's dropping to the low side of the hole, and you're trying to pull it through, and then that's causing tight hole. One mitigator, well, there are a few mitigators for that, and one is trying to ensure the wellbore remains stable, so you don't get the enlarged sections either side of these stringers. Another thing to do is managing your weight and bit as you're drilling through them, so you're not putting in some sort of micro dogleg as you come straight out of the stringer. And then another thing you can do for mitigating ledges is stabilizer design. So Paul Pastusek wrote a very good paper on physics-based stabilizer design, and it's surprising how long we've gone in the industry with some fairly, how should I say, poor stabilizer designs getting in the hole. And it's all about taper angle at the top, just wraps on the spiral, the blade sizes, but there's a lot of good, really practical guidance on stabilizer design, and a big help. Following that guidance could mean the difference between being able to pull your stabilizer through a ledge and getting stuck pulling through a ledge. So it's well worth looking at. And then whirl-induced borehole patterns. So sometimes when you come up with this as a cause of a problem event, you get some quizzical lux. It's as if you're talking about some sort of voodoo, but it does happen. In almost every section we drill, at some point you have the right combination of weight on bit and rotary speed for you to be generating some sort of borehole pattern as a result of side cutting at the bit. So Fred de Priest has written a few really good papers on borehole patterns and how to eliminate borehole patterns. And the paper there that I've referred to in the middle is specifically talking about increasing the gauge length of bits to eliminate the degree of borehole patterns. So a longer gauge bit will produce less side cutting when the BHA is going into a resonance that is causing some sort of borehole pattern. Obviously, a longer gauge bit is going to give you reduced dogleg capability, but ExxonMobil showed, and we've seen from our experience, that you can run a 4 to 6 inch gauge with some gauge relief on your bit, and still get up to about 5 degree dog legs in most 12 1/4 or 8.5 inch hole sections. So that paper's definitely worth looking at, and I highly recommend that. And then, so you can see over on the right of this slide, whirl is best thought of as being like a sine wave that develops in the BHA when the string's rotated, and the bit is part of that sine wave, and as a result, all BHAs have some amplitude of wave, and as a result, all the bits are going to be affected by that whirl. So regardless of what the LWD tool is telling you in terms of shocks and vibrations, you can still have this pattern being generated. I had a stuck pipe event offshore California where we were pretty certain we had some sort of borehole pattern being generated. Then we picked up off bottom. The pipe was just jammed, stuck. We still had circulation. There was a slight increase in standpipe pressure from prior to the stuck pipe event. Still had circulation, but we had no movement in any direction. And it was immediately after just coming up off bottom in a fairly firm formation. So we were pretty confident that was generating, that was a pattern that we got stuck in as a result of whirling, so a whirl-induced borehole pattern. So that covers all of the main root causes that we identified in the 50 problem events that we reviewed. So I hope I haven't gone too fast, and I tried to cover as much as possible on the mitigators. We go into a bit more detail in our training courses on pretty much all of those areas, but I think that's probably enough today. But I'll be happy to take any questions if anybody's got any.
Yes, sir. I have compiled some of the questions from my colleagues. Well, first of all, they wanted to know about Merlin ERD. Is it a multinational company or is it only working in UK?
I'm sorry, could you say that one again? I'll just turn my...
Okay, I'm saying that first of all, they wanted to know about Merlin ERD. Is it only working in the UK or is it also the multinational company?
Oh, right, okay, no. Yeah, sorry, I didn't give any information away on Merlin ERD. But yeah, no, we work all over the world. In fact, we have 80% of our work is overseas and 20% is in the UK.
Okay, so as you told about the whole cleaning problem, yes, what do you think?
Yeah, so yeah, no, we work anywhere. Nowhere's too hot, nowhere's too cold. Wherever we're needed, we'll be there.
Okay. So there was a topic in which we are you were teaching us about the time-based instability with water-based mud. So time-based instability, the thing time-based is a bit confusing to some of the people. So if you can bit clarify it.
Okay, yeah, no problem. Um, so when we're talking about instability, we're really talking about compressive failure of the wellbore. So the pressure inside the wellbore that's being produced by the column, the column of drilling fluid we have in the wellbore is inadequate to prevent the stresses around the wellbore from collapsing, from crushing the rock and generating compressive failure. So um, one thing that happens in the wellbore is sometimes in shales you'll get mud or you'll get water invasion into the capillaries of the shale, which weakens the rock. So the rock is then weaker, and it effectively loses its tensile strength. So that makes it easier. You then would actually need more pressure in the wellbore to keep that wellbore stable because you've just weakened the rock. So that weaker rock will fail earlier. So this over time, water-based mud can then go into the shales, and you'll hear people talk about you know swelling shales, but really it's a capillary effect. It's water infiltrating into the capillaries in the shale, which destabilize it, and it just goes soft and mushy, loses its tensile strength, and it will then fail a lot earlier. And that's a time-dependent factor. Whereas you don't get that with an oil-based mud.
Yes, oil-based mud is always better than the water-based mud.
Yeah, in most situations. Yeah, I agree.
Sir, when we are doing the ERD wells, there are a lot of big horizontal section with it. So, is it a very expensive for us to use oil-based drilling fluid, or is there any substitute in which we can use the water-based muds?
Yeah, I mean, there's yeah, I mean, oil-based muds generally are more expensive. But a good water-based mud that's really properly inhibitive, can be close to an oil-based mud. So, I mean,
What do
really,
you, is there a concept of the nanoparticles in your drilling fluid?
sorry, say that again, please.
Is there a concept of nanoparticles in your drilling fluid over there, like graphene oxide?
Nanoparticles.
Yes.
Uh, um, no, I'm not really familiar with the use of nanoparticles. We were involved in one nanoparticle lubricant trial, but other than that, that's the only nanoparticles that we've been involved with.
What was its name, sir, if I can ask?
Well, it was kind of a prototype fluid. It was an experimental project. It was just given an experimental name, and it's still not commercial. So
Okay.
can't really share that.
It's always like a secret with things in the oil and gas industry. Data is very important for us. So coming up to the next question, there was a differential staking which is due to the overbalance condition. So what is the physical phenomena that happens in an overbalance condition which makes us achieve this differential staking?
I'm sorry, I didn't catch the end of that one.
I am asking you that overbalance condition it's important for us to obligate the kick which we are having in the offshore or on the onshore field. But why is it happening that the differential stacking is coming out as a result of overbalance condition?
I'm sorry. Why is what happening?
Overbalance by achieving overbalance condition, we are having differential stacking.
Yeah, I mean, so I mean, I'm sorry, it was just the background noise that was causing a bit of an issue there. But yeah, so operators are running high overbalance for a number of reasons. I mean, really, um, often for wellbore stability, for well control, and that's pretty much it. Yeah, wellbore stability and well control. That's why they're running high mud weights. And they're both really legitimate concerns. When you think about, what as a drilling engineer, or a company man, drilling supervisor, what's really going to spoil your day? Well, a well control event or a stuck pipe event. And when differential stickings are high risk, and well controls are high risk, then you've got two conflicting requirements. You want to run your high mud weight to mitigate your well control, but you might want to run it a bit lower to mitigate differential sticking. So you've got two conflicting requirements. So it's challenging. But
It's
if you understand what the other risk factors are in differential sticking, then you can deal with them, and you can leave the mud weight. You can get away with a really high overbalance if your mud's in good condition, so you don't have thick and fluffy filter cake. If you're closely monitoring, you pick up on connections, you break over torque after a connection, and you break over weights. You can see the hole's getting sticky. Then you've got the opportunity then to just condition the hole, get the stabilizers over it, get the bit over it, and then take off some of that thick and fluffy filter cake, get the bridging solids in the mud that you need to quickly bridge over the permeable formations, to lay down a thin, well-conditioned filter cake. So there is lots you can do to mitigate that differential sticking without compromising wellbore stability and well control.
Yes, it's always challenging, but both the problems are of the opposite nature, and with that, there is a non-profit time with it.
Yeah. I mean, it's always challenging. I mean, there's a danger that I make this sound too simple, because there's always conflicting requirements. And when you reduce the risk in one area of the well, you're often then increasing the risk in another area of the well. But that's the drilling engineer's job. That's what he's paid for, to balance
Yes,
those risks and to
uh,
fully understand the risks.
you're right. With that, I guess I have completed with my questions. So, if you have any message to give us to our students, it would be very great of you.
Yeah, you know, I've given some SPE papers references on towards the end related to the wellbore stability. One of those was two of those are written by Fred de Priest. So Fred de Priest was the chief drilling engineer at ExxonMobil, and also he's now professor of petroleum engineering at Texas A&M University, and he's written some excellent papers that are quite accessible, so quite easy to understand. And I would highly recommend reading some of those papers, and then some of the papers that he references, then moving to those. So so I would just, my general message is, read around your subject a bit. Don't just stick to your course material. Read around it. Find out more. Be curious. Ask questions. And don't be afraid to ask questions.
Oh, that was very nice of you, sir. I'll be ending my live broadcast, but you don't go anywhere. I have a bit talking with you.
Okay, my pleasure. Thank you very much.
Thank you. Thank you.